When I talked about floats, I said one of the reasons why we have both integers, or ints, and floating point numbers, or floats, is because of precision. Now, the precision issue is actually just a little bit subtle, so I wanted to cover it here in its own video so you can see the essence of what's going on. Here's a little 3-line program that I'm going to use to demonstrate the basic idea for you. The first line declares an integer, which I'm calling isum. I'm going to add up some numbers, and so I call it a sum, and I'm using I because later I'll create a floating point version, and I'll call that fsum. So okay, I create an integer called isum, and I give it an initial value of 0. Line 2 is an assignment statement. So we know we start on the right-hand side. We look at the expression isum plus 1. Isum at this point has the value 0. So we compute 0 plus 1, which is 1, and stick that into isum. And then the final line is a print statement. And I talked about print statements in the print video. If you haven't seen the print video yet, all this line is doing is it's telling processing to print the string isum equals, followed by the current value of isum, into the console area at the bottom of the window. So I'm going to run this in a second, but before I do, I want you to stop and think for a second, and you can pause the video. But what do you think is the value of isum at the third line? Well, we just talked about it. I think you know, but just check with yourself, and then I'll run the program. So here's the output, and it's no surprise. We started out with 0, we added 1, the result was 1. Great. Okay, let's now copy and paste this line with the addition, and I'll now add 1, and then I'll add 1 to it again. So again, I'm going to run this. Before I do, ask yourself, what do you think isum is going to be? I'll run the program. And here in the output, we see isum equals 2. Great, well, we added 1 twice. So just for fun, I'm going to paste this line 5 more times. So I have a total of 7. So I'm adding 1 7 times. What do you think we're going to get? Let's run it and find out. And there's our output. Isum is 7. Now this should be no surprise. It should all at least make a certain amount of sense to you. That's integers. So let's compare this to floating point and see what happens. So here's the same program with minor differences. I've changed the name of the variable from isum to fsum because I'm declaring it to be a float. And instead of adding 1, I'm adding 0.1 because it's a floating point variable and I can add a little fraction to it. So I'll run this program. Again, ask yourself what the output should be. And there's the output, 0.1. Perfect. So I'm going to stop the program, and just like before, I'll add 0.1 2 times. What do you think the output's going to be? If you thought it was going to be 0.2, I agree with you, and so does processing. So just like before, I'm going to stop the program, and I will paste this line 5 more times. 1, 2, 3, 4, 5. Now I'm adding 0.17 times. What do you think the output's going to be? Let's run it. Well, isn't that interesting? That's not 0.7. It's a tiny little bit bigger. Just the tiniest bit. 5 parts in 10 million. But it's a little bit bigger. And that is the trade-off with floating point numbers. Integers can hold any whole number within their range, and they represent that number precisely. Floats have a much larger range, and they can store fractional information. But the price you pay for that flexibility is a tiny little bit of inaccuracy. Now, this isn't a problem with processing or your computer or the underlying operating system. This is how floating point numbers work in every language on every computer. It's the nature of the beast. It's the trade-off that we get for being able to have a huge range and fractional components. And believe me, people have sweated this for many, many, many years. And this is the compromise that people came up with, where they traded off those benefits for this tiny little bit of inaccuracy. So the question is, do we care about this tiny bit of inaccuracy? And the answer is almost always we do not. Almost never. When you're drawing graphics, when you have things moving around on the screen and you're responding to mouse presses and you're running your processing program, you are never going to be worried about this tiny little bit of inaccuracy. It just won't be an issue. I have written thousands, if not more, of programs in processing, and I've used floats for all my fractional numbers, and I've never had a shred of a thought that there was an issue with accuracy, even though I know in the back of my head my numbers aren't exact, but they're so close, it just doesn't matter. So if that's the case, why are we talking about this at all? Because there is one time where it really makes a huge difference, and that's if you're testing the value. Let me show you how to test the value of something. Here's our integer version once again. Now I'm going to show you a construction for testing the value of isum, and I'm jumping ahead. We are going to talk about this, and we're going to talk about it in detail, but just roll with me for now. I'm going to write something that says, I'll write it out in English first. If isum is equal to 7, then print isum is 7. And otherwise, I'm just writing English here, and I'll replace that with processing. Print isum is not 7. Now I'm going to turn this into processing. And don't worry about it, we are going to cover this later on. But I'm just going to replace this English, if isum is equal to 7 then, with a little bit of processing. That's how you write that. Note that between the isum and the 7, there are 2 equal signs. We will talk about the reasons for that later on. The word otherwise turns into this, and then I put a closing little curly brace at the very bottom. And I'll make my window a little bit bigger so that we can see the whole program now. So all we're doing is we're testing the value of isum. And if it has the value of 7, we print this. If it's not 7, we print that. Well, we know what's going to happen. I'll run the program. And of course, isum is 7. And if we look at the output, it tells us isum is 7, which is perfect. Of course, the reason I'm doing this is so I can do the very same thing with the floating point version. And all I'll do is come down here and paste those lines directly from the other program. And I was using isum there, so I'm going to change fsum here. And I'm no longer looking for 7, but I'm looking for 0.7. So now let's run this program. Well, first ask yourself, what do you think is going to happen? I'm asking it, is fsum equal to 0.7? So let's run it. And here's the output. Fsum is not 0.7. Well, that's right. It's not. It's 0.7000005. Now, there's no way for us to know before we run the program what that little bit of noise is going to be. Maybe it's going to be 0.7000004 or 3 or 9. It's all we know is it's going to be a little bit off. So testing the value of something is where floating point numbers run into trouble, because we don't know exactly what they're going to be. And when the computer tests to see if two things are the same, they have to be exactly the same. So suppose that this program was counting up the score in a game, and someone wins when they first get to 21 points. By the time we add in 0.1 enough times to get to 21, fsum probably won't be exactly 21. Right? It'll be 20.9999999 or 21.0000001. It'll be some tiny little bit above or below. And so if I ever test if fsum has the value 21, that will probably never match. It'll never be exactly 21 because it'll always have a tiny little bit of noise. And that's a problem because we do this kind of thing all the time in programming, and you want your tests to work. Well, we've seen the version that works. Here they are side by side They're almost the same program, except that the integer version, the test works. So we use integers almost always when we're counting and when we want to test for an exact value. And we use floats for everything else. And that's why we have ints and floats.